Exponential functions. An exponential function is when an exponent is a variable. All right, so an exponential function, if you'll look, is ab to the x. ab to the x. You'll notice that the x is in the exponential place. That is an exponential function. The number that is the large number, that's called the base. The tiny number, that's the exponent, right? All right, so we have a base, which is your b, and then we have the x, which is the exponent. And they show you this graphic. I am not going to make you graph exponential functions. Honestly, the truth is that for most of your graphing, you're going to use a graphing calculator if you absolutely have to graph something and need a picture of it. But for your polynomial and your rational functions, I really needed y'all to have a strong grip on that for my calculus kids, because I really need you to have those pictures, right? But for exponential functions, the picture is that it's not linear, okay? So think about how linear tracks. Linear tracks just steady, slow and steady, up a particular slope. Exponential looks like this. It shoots up, or if it's decay, it shoots down. That's why we have the term, it grew exponentially. What do we mean by that? It shot up, right? It just completely shot up. And so that's what that function looks like. You can see that it is no longer this steady little slope. It's this, we're going to start and then we're going to take off. All right, that is an exponential function, and that's what they look like. All right, the most common thing that you are going to see with exponential functions is compound interest. Compound interest and exponential growth and decay, which are the two problems that we actually do in this section, is where you see this the most. You'll see compound interest in obviously like a business class. If you were to go to college and take business, you're going to see these type of formulas. If you go into any type of science or chemistry, you're going to see exponential growth and decay. And for those of you that have finished chemistry, you probably did half-lives and stuff in chemistry, maybe. That's exponential. Those are exponential functions. So compound interest, $30,000 is what he invests. 6% is the APR, or the return on the investment. They want us to calculate this balance after 15 years, which with each of these, and we are compounding it annually, quarterly, monthly, daily, continuously. So the two functions that you see up here, one is compounded. It says annually, but that actually means like an n is the number of times a year it compounds. So this first function is given when you have like, it's compounded this number of times per year. That's the function you're going to use. P represents the principal, which you initially invest. R represents your interest rate, which is that 6%. Remember, you have to put that in decimal form. So that in this case would be 0.06, right? N, the number of times per year it compounds. This really matters because you'll notice as we do this, that the more often it compounds, the more return you get, which by the way, works against you when you take out a loan. So you take out something like a credit card, they compound every 30 days. Okay, that's once a month they compound. That is why credit cards roll, because the next month you are paying interest on your interest. It's called compound interest. It works really great when you're investing. It works really poorly when you are borrowing. So number of times a year that it compounds. And then up here in the exponent form, you see the number of time it compounds again, multiplied the number of years you are compounding. Okay. So this is, I am given an amount and I'm saying it compounds this many times per year. All right. The other one, which people normally remember because it looks like a word, right? PE to the RT. These all represent the same thing, except this is compounding continuously. It is continuously compounding, okay? And so the P is, again, your principal. The R is your rate. The T is the number of years. And the E is your natural number E. It's like 1.17. I don't know. People recognize this. E is like pi, okay? It's a non-terminating, non-repeating decimal. Okay, it's just represented by this little guy so that you know what it is. It's called the natural number, all right? Natural number, E. And it's, so if you put in your calculator, E times 1, you're going to see that little 1-point decimal, right? It's just a number, but you use that number and take it to that power. All right, so let's look at this guy. $30,000 is invested. So a couple things, and I say this because sometimes people don't naturally know this. If it is compounded quarterly, how many times a year is that? 4. 4. There we go. Monthly would be, and daily would be on a non-leap year. There we go. Okay. So sometimes they'll do, semi-monthly. That means twice a month. Bi-weekly. That means every other year, which is 26 times a year. By the way, there are 52 weeks in a year. So just pay attention to those terms and make sure you actually know what that stands for numerically, okay? So really for these, you just fill it in. If I am trying to find what the return was, I am going to say, let's say for annually, 30,000. 1 plus my interest rate, 0.06. Number of times it compounds a year if it's annually. Well, that's 1, okay? And then raised to the number of times per year for 15 years. That would be annually. Let's say we did it monthly. Monthly is going to equal that 30,000. 1 plus 0.06, and now my number of times is 12. And then 12 times 15, right? Continuously, now I'm going to use this one. Continuously is going to be 30,000 times e to the 0.06 times 15, okay? So what I want you to do is I want you to try those 3 in your calculator and make sure you know how to put it in a calculator. You will see growth and decay. The growth and decay models look very much like your other model, except you really only have annually or continuously. And honestly, for growth and decay, 9 times out of 10, you're going to use continuously. Rarely have I seen it compounded annually. In 1963, the U.S. Fish and Wildlife Service counted 487 pairs of nesting bald eagles in the 48 contiguous states. After being placed on the U.S. endangered species list in 1967, their number increased to 3,035 nesting pairs in 1990. Assume exponential growth. Find the average annual percentage increase in nesting pairs from 1963 to 1990. Then use an exponential growth model to predict the number of nesting pairs in 2006. All right. So I will say when they do years, very often they will have like, this is my starting year, and then just count the number of years since then, which is what they did here. So if you'll notice, it says, let time 0, t of 0, or your initial, be 1963. So because that's when they started, instead of using like 1963 and 1990, they are going to use the initial year as 1963 and 27 as 1990, because that's 27 years from 1963. So then your initial amount, so at time 0, there were 487, and at time 27, there were 3,035, all right? So they said annually. What is the annual increase? The only time that you're going to see something like this is if they verbally tell you annually, okay? If they want a growth rate, you're typically going to use your E, okay? Because like bacteria growth is like the one they love to use. It is going to be a continuous growth. Bacteria growth is going to be a continuous growth. With population even, it can sometimes be the continuous unless they do it year over year like they've done here. So because they said annual increase, we are going to plug it into this guy. Well, my ending amount was the 3,035. So I have 3,035 as my ending amount. My initial amount was the 487. The rate is what we're trying to find. We don't know that. But we do know how many years, which is 27. And they actually show us to solve this with roots. We're actually going to learn in the next, section 4, I think, to solve it with logarithms. So the first thing I want to do to try to isolate this r is to get rid of that 487. And so I am going to divide both sides by that 487. So I have 3035 over 487 equals 1 plus r to the 27th. And just like anything, you need to take the root. Now, on your calculators, you can take a 27th root. It's really tiny. So in your calculators, you actually you should have like an x to a y, and then above it, that's going to be your root that you can take. But I'm just going to show you the process right now. We're going to move to doing this with logarithms, which I think is easier. So if I do the root, over here I have 1 plus r, over here I have this root of this guy. And then, of course, to solve, I'm just going to take that root and subtract. And I think they have approximately 0.0701, which means it was a 7% growth rate. Now, I will tell you that when you're solving for like within the parentheses, you're going to start seeing a pattern here that just like your root cancels out your exponent, we're going to find that your log cancels out your exponent as well. And so there is a connection between your logarithms and your exponents here. Half-life, there we go. That's what it's called. The half-life of carbon-14 is estimated to be 5,730 years. Okay, what that means is it takes 5,730 years for the amount that you start with to cut in half. And as you can imagine, if you've ever tried to cut a piece of paper in half and you keep cutting it in half, it seems to go on forever, because it kind of does, right? Basically, you're taking that 1/2 to a power when you're talking about a half-life, because you're saying 1/2 to this power, okay, 1/2 to the next power, okay? You're basically multiplying by 1/2 because you're dividing this guy in two, all right? So every time you multiply it by 1/2, you're taking that 1/2 to another power, okay? Organic remains near Ailes stones in Sweden have been used to date the monument near AD 600. Suppose a sample of the remains contains 68 milligrams of C14. Estimate the original amount in the sample 1,400 years ago. Predict the amount of C14 remaining in the sample 50 years from now. Okay, so we are going to use the continuous breakdown here, your continuous. For this particular one, we are not multiplying by it. We are actually dividing by it, by the half-life, because it is a half-life. So you have what you're trying to find. You have your initial. This is going to be 1/2 because we're talking about half-life. You have your time, and you have what happens. Your rate is actually divided. It's going to be 1/. So while you're multiplying by your rate is actually 1/, that amount, because it's a half-life, okay? So you're actually reducing it by that amount. So for this one, we do not know our initial. That's what they're actually asking, the original amount. We know how much remains. So how much remains is actually going to be this piece of it, 68. We don't know the original. We know it is a half-life. We know the number of years, 1,400 years. And we know how much it decays in a half-life, 5,730. All right, so while this is a crazy number, it's really just being multiplied. So how do I solve for this initial amount? I just divide by that big crazy thing, right? Divide both sides by that 1/2 to the 1,400 over 5,730. In your calculators, it would look like this, 68 divided by, and then you want to do 1/2, or, I mean, obviously in your calculators, 0.05. And you want to do 1,400 divided by 5,730. Now, I will say your calculator should do this first, right? Make sure it does. But if it doesn't, you can put parentheses around that piece as well. You should get approximately 80.5 milligrams. By the way, it started out with 80.5 milligrams. 1,400 years later, it's at 68 milligrams. That's how half-lives work, right?